Hi, so am I audible, Rajni? Could you please confirm, or anybody else? Okay, so let us start the session. Let me present my screen first. Anyone please confirm whether I am audible or not? Okay, great. Let's move on. Thanks. So today we are going to see design of induction machine, right? So that is week 4 content. So we will start with certain problems first. So we are given with two machines with all the dimensions in the ratio of k to 1. Machine 1, machine 2. Okay. So dimensions of machine 1 is 1 is to k. Okay, all the dimensions, right? But speed, flux density, and current density are same. Okay. Now we have to find the ratio between kVA rating of both the machines. Can we find out? So what is the kVA rating of the machine generally? Input power divided by power factor, right?
Perfect. Yes, perfect.
And can we describe input power in terms of output power?
T into omega.
Yeah, T into omega, right? So I just want to write in terms of efficiency.
Efficiency. Okay, pure efficiency.
Okay. And finally, it will be torque into omega divided by efficiency into cost. Okay.
Yes, sir.
So only parameter which depends on the dimension is torque here, right?
Hmm.
torque is directly proportional to d square L.
D square L. Yes.
Yeah. And other thing, in torque equation also comes electric loading.
Electric loading into matic loading also will come. Sigma is there, no?
Yes.
Pi, pi by 2 into d square into L into sigma. In that sigma is A into B.
Yeah. Could you please repeat? Pi by 2
Pi by 2 into d square into L into sigma.
into sigma. Sigma is here stress.
A
Sorry,
into, yes,
shear stress.
shear stress.
Yes. And shear stress is nothing but the product of magnetic loading into electric
Electric
loading.
loading.
Okay, this is just product. Now, electric loading, we know it depends on the current, right? So
And
first
number of
we are,
conductors.
yeah, and number of conductors, right? But which parameter does depend on the dimension? Current or number of
A
conductors?
current for a given area. I mean, current, and sir. Current.
Exactly, exactly. So what I am referring here, that torque is already proportional to d square L along with electric loading, right? A.
Mm.
And A is directly proportional to current. And
Yeah.
current is directly proportional to current density, right? Which is delta or J you can, right?
Mm.
So there is an expression of ampere conductor loading in the machine is uh, I into Z divided by pi d. Okay, so total number of conductors and current flowing in a single conductor divided by pi into d, which is circumference of the machine. Okay, and I we can write in terms of area as J into A, right? Divided by Z pi. And area is proportional to d square. So ampere conductor loading is proportional to d square divided by d. It will be finally d. Right, so this d we can replace here with a, and can we write torque is directly proportional to dq into L. No, torque here we have to say power. Okay, and all the parameters are scaled with the factor of k. So p2 by p1 would be k4 by 1. So this ratio would be equal to k raised to power 4 is to 1, right? So kVA rating is proportional to dimension of raised to power 4. If you are changing the dimension of the machine by ratio k or the scaling by a factor k, then your torque and power will be scaled by the parameter of k raised to power 4. Okay, is it fine? Any doubt in this?
No, sir, not it.
Okay, so let's move on to the second problem. So air gap length is is we have to find out, and the machine parameter is pole is equal to 4, three-phase induction motor with a pole pitch of 0.2 meter. We have to calculate air gap length at G with Lipos method. What is the expression of air gap for Lipos method?
Yes. Close my fist.
If you have gone through the lecture, so the expression is pole pitch into under root 2 times number of
Uh,
pole
yes. So, there is
into
Uh, G plus square root of G dash. There is some relation also is there with G. That's
Yeah, yeah. With G, that is
LD,
another.
LD with LD, LD. Sorry, LD.
Yeah, so that is the Say's method.
Okay.
G plus 2 times under root LD. That
Ah,
is
yes, sir.
Say's. That is Say's method. But do not get confused between two of them.
Okay.
So this is with LiPo,
Lip.
and if you multiply 3 times in its power minus 3. So this is the expression of air gap for LiPo's method. Okay. So can we
Okay.
calculate now the air gap?
Yeah, yeah. Why not?
Wall pitch is given zero point 0.2 into under root 2 into number of poles 4 into 3 into 10 to the power.
It's a 1.697 into 10 power minus 3.
Exactly 1.697 mm. Okay.
Yeah, ma'am. Ma'am. 1.6.
So basically, according to LiPo, how much air gap you can keep in the machine, that depends on how much is your pole pitch or how much bigger your machine is. Also, how many number of poles. So only two parameters he has considered.
Mm.
One is pole pitch and other is number of poles.
Yes, sir.
And in phase method, that axial length as well as stator bore diameter both are considered. So that is the difference between them.
Can we means calculate in that way also one time? But
Yeah,
we
yeah,
don't know
sure,
about
sure.
that, no?
Yeah, but we do not know how much. Okay, we can
But
start
we
with,
have pole pitch, no? Pi d by we can be
yeah,
pi d by p 1.2.
with phase method. Z is equal to zero point 0.2 plus under root P, 2 times, right? 2 times
Ah,
into.
2 into square root of d into s.
So how much will it be?
Pi d by equal to 0.2 number of poles divided by p.
Neither we are given the axial length nor we are given the diameter.
But the
But
diameter we can calculate, no? And there is some relation between no, length and diameter of the DC induction
in the
machines.
okay, so you can actually approximate if you are going to design it.
Approximately we can tell, yes.
Yeah, yes.
Approach. Okay.
So how much will be the diameter? What should be the expression for diameter? We are given the pole pitch.
Pi d by p. Pi d by p, no, sir. Pi d by p equal to
Yeah, tau is equal to pi d by p. So here it will lead to 0.2 into 4.
0.254. 254.
0.254 you are saying?
Yes, sir. Yes, correct.
0.254 meter. Okay, thanks.
DL by D ratio is 0.2 times, no?
L by D ratio is 0.2.
0.2. 0.2 for
Point,
induction machines. Sometimes.
that is too low, I guess.
Yes.
0.2, I think it is too low. Are you sure 0.2 is there?
Actually, for DC missions, we used to take zero point 0.6 to 1.2. You can go for wiper mode, it's a more than a diameter. No, so for induction missions, better we go for zero point 0.2, zero point 0.4. Like we cannot exactly say that approximately.
Since induction machine we are considering by default as a radial flux machine, right?
Okay.
So generally
Length
in
is more.
radial flux machine, no, diameter is more.
Yes, diameter is more. L by D ratio. L by D ratio, sir, not D by L by D ratio.
Okay, L by D you were saying 0.2.
L by D,
Yeah.
L by D.
Oh, yeah. Still, it is too high, but anyway, it is considerable. Right. D by L is almost 5 times. So diameter is almost 5 times of axial length. But yeah. So L we can calculate zero point 0.2 into 0.254.
0.050.
0.050.
It's less only.
Okay, it's reasonable. Yeah, zero point 0.2 is reasonable. Yes.
Diameter is 2.4. Here it's 2.00. It's a 0.427 is coming, sir.
Yeah, 0.427. So it's a two less air gap for such a
Such
high
a bit.
dimension of machines.
Yeah.
But still, 254 mm and 50 mm. So still, it is possible. It is not that this value is impractical. It is possible. And on the other hand, with LiPo's method, this 1.697 mm is on too higher side,
Hmm.
and with Say's method, it is on too lower side. So I don't know which one to go ahead with, but if you are designing machine, so generally it also depends on which type of machine you are considering. If you are considering a squirrel case, then 0.5 mm air gap for this much dimension should be fine.
Hmm. Yes, sir.
Yeah, and also it depends on, see, not only dimension, how much electric loading and magnetic loading is present in the machine. So how much kVA rating of the machine, that also determines.
Hmm.
So, yeah,
Okay, sir, fine.
so let's. I hope there is no any doubt in this part. Any question? Any question is coming in your mind?
No, sir. It's a very clear actually.
Okay, okay. So let's move to the another problem.
Hmm.
Here, we are given the slot area, total slot area of an induction machine. Okay, and a single layer winding is mentioned. And we have to find out that for AWZ12 wire size, how many number of conductors can be filled in the slot area? And slot fill factor we have to also consider here.
But that's
So how much is the typical slot fill factor for round conductors?
45%, sir.
40 to 45%, but in this problem it is mentioned 0.5.
Okay.
Okay, and yeah, so that's all about this problem, and we have to find out how many number of conductors could be filled in the slot area. And also, since if you have the access to data sheet, you can also Google it. I am giving you the area for that and dimension for AWZ12.
Mhm.
So AWZ12, its diameter is
American Bible. Second.
2.053 mm. Okay, and its area is 3.31 mm square. Okay, so this is the area of the wire and diameter of the wire.
Mm.
Okay, now since we are given with the total slot area of the induction machine and we are given with the fill factor, so we will have certain area in which total number of conductors could be filled, and that is the 50% of the total area. So could you explain why is it like? I just want to understand your understanding. How much will be area that could be occupied by the conductors, and why only 50% if it is, and not whole the portion of the slot?
Actually, we cannot do because while we are physically winding the mission 9 slot, it's difficult actually because that's a round wire, no?
Right, right,
If it is a rectangular wire, then we can go for the till 90% also slot will we can go because it's that one. And when coming to this one, tension is more actually. We are unable to wound that.
right. So if let's suppose your slot is like this, and if you have circular wire, round
And
wire,
this slot line also is there.
yeah, and slot insulation, wire insulation,
Wire
other
insulation.
factors are wedges are there, right?
Edges are
Wedges,
there. Yes.
yeah. So by considering all those factors in account, and also these area are unused, you cannot fill those area, right?
Yes, we cannot be.
So that is why with round wire, generally it is considered between 40 to 50%, and with rectangular conductor, it is considered nearly towards 70% also.
Mm. Yes, sir. Correct.
Yeah. So now we have active area is slot fill factor times the slot area. Okay.
Mm.
So it will come out to be 816.41408.15 mm square. Okay. So this is your active area in which conductors will be filled. Now, area of wire is given here, right? Now you can calculate, you can divide to calculate the number of conductors. Area, active area divided by
Right? No
area.
area.
Yeah. Any
Total
doubt
slot.
here? Okay. So active area is 408.15 divided by wire area is 3.31. So I think now we can calculate.
Yes.
So
123.30.
123.3.
30.
So approximately 123 conductors could be filled per slot. Okay.
Okay, sir.
Okay. Let's move towards the
Next
next
one.
problem. So here, main
So
dimension we have.
123.308 means we have to take whole number. No, 124 na, sir. We can take 124 conductor.
Uh, if 123.3 it is there, yeah. So you can take the round of figure from the
Yes,
options if
124.
options
Even
are
number.
given. Even number is not mandatory here. Why you are saying even number?
We do one turn like this. So when we did one turn, it is having two conductors. We unable to
Hmm.
do half turn, no? So we can do full turn.
Okay. Okay. I got it. So, uh, see, one conductor in a slot and in other 123 conductors in the other slot. So total two 246 conductors.
No, what I'm telling means actually when we are winding that one, we took the slot. For example, to okay, we can go for the 220. For example, say tooth concentric. When you did
Hmm.
winding, na, we will do one turn, full turn.
Okay.
Each turn having two conductors. This side one conductor. This
Yeah, each turn is having two conductors, right?
turn is composite two conductors. So we do in form of turns only. Na, we like while you are doing
So
winding, we go for turns. How many
yeah,
turns?
right, right. So if 123 conductors in one slot, there will be 123 conductors in other slot.
Yes.
So total 246 conductors will form 123 number of turns.
Okay.
So number
Yes. Yes,
of
fine, fine.
conductors could be odd. Okay.
Okay.
I understood your concern that
Because I feel like if there is a turns of the turn, if turn odd, but conductors never be odd number. No? For example, say turns three.
hmm,
Three is the odd number, but conductors are three to the six conductors.
okay, in that way you are saying.
It's a multiple of two, no? So composite will be even number conductors.
Okay, I got your doubt. So you are saying one term
Mm.
comprises of two conductors.
Two conductors.
Yeah. So, and these two conductors, okay, these two conductors are distributed in two different slots. So let's
Yes.
suppose, so here it is one conductor, it is coming from here, and it is coming from here.
Yes.
So
Yes.
here
One.
in this slot, one conductor is placed, and it is
Mm.
possible. It is possible kind of finding. Are you getting my
Yes.
point?
Yeah, got it, sir. No. Okay. Okay. Got it. Yeah.
Yes.
I got it.
It's good that you are asking such type of questions. It is showing your understanding that how you are, visualizing the conductor kind of. Okay.
Okay.
Yes. Okay. So the next thing is, okay. So we are moving towards the next problem now. Okay. Any further doubt in this part?
No, sir. Clear.
Okay. Yeah.
Yes. Fourth.
So we are moving on to the fourth problem. We have to find the main dimensions. What do you mean by main dimensions? Nothing but D and L.
L. Yes.
Okay. So we are given with 17 kilowatt, three phase, two pole, 400 volt, 50 hertz, 2900 RPM. Okay. A squirrel cage induction motor. Efficiency is given as 88%. And it has a full load power factor of 0.9. Magnetic loading is given 0.5 Tesla. Electric loading is given 2500, 25,000 ampere turns per meter. Okay.
Okay, sir.
Ampere conductors per meter.
Yeah.
Or we can also write as ampere per meter. There is no harm in that. Ampere per meter. Now, rotor peripheral speed is mentioned as 20 meter per second.
So pi d n by 60 they given 20.
Uh, which parameter you are saying?
Peripheral speed means pi d n by 60 only, na sir?
Yeah, rotor peripheral speed you can uh,
R omega okay. If you
omega, and
like
omega you can write as 2 pi ns
2
by
pi n by
60.
60 and from
Yeah.
that one pi d n by 60.
Okay. Okay. Let us see. I do not. I haven't remembered that expression, but let us derive that.
Okay.
And it is using a star delta winding. Star delta starting, and no ventilating ducts are required for this. And SPP, slot per pole per phase, is 3. Winding factor you are also given with. Winding factor is 0.955.
Fine.
Winding factor is nothing but the multiplication of pitch factor into
Yeah.
distribution factor. Okay.
Yes, sir.
Now we have to calculate the dimension. So now how to proceed? How to proceed with that, and what should be the expression where this dimension will come in the picture? In torque, we know d square L is there,
Mm.
right? So
Yes, sir.
somehow, if we can calculate torque of this machine, we will be able to calculate d square L parameter.
Yeah. We can calculate d square L.
Okay, and again in rotor peripheral speed, Vs is given, and from there R omega. So again, from there
There
diameter we
also
can
we can
calculate
get d.
d.
And
Yes,
all the
right,
diameter we know we can like calculate the length.
right, right. So first we should try to calculate torque here,
Yeah.
right?
Mm. T equal to pi by 2. That one only. D square. D square into L into A into B.
Yes,
D into D square.
and torque is also power by omega. So
P by W.
power
Here
we are
70
given.
kilowatts we can
Yeah,
take now.
right, right. So power we can take 17 kilowatt,
17 into 10 power 10 power 3 divided by
2 pi ns by 60.
2 pi n by 60.
In terms of RPM,
Hmm. Peripheral from peripheral speed. Okay, we can.
so in terms of peripheral speed also we can calculate. So V is equal to R omega, and it is nothing but R into 2 pi n by 60. Okay. So 2 pi n by 60 we can equate as
2 are equal to d pi d n by 60.
V by R, right? So V by R or V by 2V by D. So this omega we can replace with 2V into D. Okay. And this parameter is given to us. So let us move ahead step by step. So pi by 2 into magnetic loading is zero point 0.5 Tesla, electric loading is 25 kilo ampere per meter into d square L is equal to 17 kilowatt divided by 2V into D. Okay.
Okay.
Now here 1D and this D will be cancelled out. So DL we can write in terms of this 10 to the power 3 and 10 to the power 3 will be cancelled. It is nothing but 17 divided by 2V into 0.5 into 25 into pi by 2. So this also we can cancel out. So we will get the value of DL from this expression.
17 by 2 into 5
And V also we are given as 20 meter per second. So V also you can write as 20. Now I think you can calculate.
Yes. 0.0216.
0.0216
Correct? I will check once.
meter square it will be.
0.0216 correct, meter square.
So we have the value of DL. Now we can calculate the value of D. Okay. So V is equal to R omega. And V we are given 20. R we need to calculate. Omega is nothing but 2 pi n by 60. And here n should be nr, right? Rotor speed.
2900 RPM.
Yes. So R will be 60 into 20 where 2 pi nr is 2900. Okay. So radius of the rotor will be 1200 2.2900. It will be
0.0658.
0.0658 meter. So D will be 2 times of R, that is 131.6 mm is the diameter of the machine. So the diameter we have calculated now, and we have another equation which comprises D and L.
From there we
Right.
can get L value.
Yeah. So here we can get L value, that will be 0.0216, where 0.131.
0.163.
0.163 is the length of the machine, right?
Yes, sir. One second, I'll check. Yeah, correct.
Correct. Okay.
Zero point
Just
one.
just re-verify your calculation if you are not sure, but this is the method to calculate. Okay. Any doubt in this problem?
No, sir.
Now let us move to the next problem. We have to find stator turns per phase in a squirrel cage induction motor, right? And the rating is given as 11 HP, 415 volt, 3 phase, 50 hertz, 1500 RPM. Okay. Again, magnetic loading is same, 0.5 Tesla. Electric loading is same, 25,000 ampere per meter. Now, efficiency at full load is 0.82. Power factor is 0.85 lagging. Winding factor is again same, 0.955. And again, same slot per pole per phase is equal to 3. Now, this time a stack length to pole pitch ratio is mentioned. That is nothing but 1.5. Okay. Now we have to calculate stator turns per phase. So to calculate that, which expression will be helpful in calculation of number of turns?
Electric loading.
Electric loading. Yeah, electric loading is given directly here, right? So
Yes.
what is the expression of electric loading?
Electric loading equal to IZ into Z by pi d.
Yeah, IZ into Z divided by pi d.
Pi d.
Okay, so here number of conductors we are not given with, right? So can you calculate number of conductors from the given information?
We know the voltage and we know the what is the rating of the machine.
Yes, yes. You are close.
Then we can calculate the current from over there. P equal to 2.
See, you are given the voltage rating, right?
Yes, sir.
And
415.
yeah, and in voltage, is there any number of turn expression there?
No.
Uh, Recall carefully.
Yes.
In induced EMF,
Is there? Yes, yes, yes.
yeah,
Number of conductor directly proportional, है ना?
right, right. So 4.44 into F by N,
4.42 pi into F into Z.
yeah. So we can write V is equal to 4.44 into F by
Into pi.
N. Okay, F by M actually. And now, since we are dealing with AC machines, right, the winding factor will be multiplied, isn't it?
Yes, sir.
So here, this number of turns parameter is there, right? And this is what we need to calculate. Okay. And this N is what?
Number of turns.
Turns per phase or per pole?
Number of turns per phase.
Turns per phase, exactly. And that's what we need to calculate here, right?
Hmm.
Stator turns per phase. So let us proceed. N is equal to voltage is given 415 volt, that is RMS. So 415 divided by 4.44. Frequency we are given with 50 hertz. IM are we given? Magnetic loading we are given.
They given 0.5 Tesla.
So phi m
Catch
can be calculated. If we are given with
B equal to 5 by
fluctuating,
A, no?
yeah, B is equal to phi by A, right? You are right. And how to calculate that A? Okay, so let me write whatever we know till now.
Okay.
So phi m we don't know yet. We will calculate it. And Kw we know that is 0.955. Okay, so we just need to calculate phi m, right? Now,
Yes.
to calculate phi m is nothing but B into A,
B into A.
into area,
A.
right? And
Yes.
B is given as magnetic loading and it is given only for the pole. So the area I have already mentioned in the last session also that it is pi dl, which is circumference divided by P. So circumference of a pole, right?
Hmm.
Okay. Now, B average we are given 0.5 into pi. Are we given with D and L? I don't think so.
No.
But L by T we are given with.
L by tau they given 1.5.
Yes, yeah.
Yeah, right.
So DL divided by number of poles is
Right.
4. So now our next objective is to calculate D. Okay.
We can calculate P now. Sir, P equal to 120 F by N. 120 F by P N equal to. From that we can calculate P, no?
In this P is given actually, no?
Given? No, 11.
Okay, P.
Plot per pole per phase they given as a 3A, but
Okay,
they
yeah. So pole number of pole we can calculate. 120 F by P.
N equal to 120 F by P. P equal to 120 F by N.
Yeah.
$1,500 RPM.
So P is 4. Okay.
5
So
4.
mm, so that P is 4, right? Now the remaining part is D and L. Now L by tau is given. Can we calculate L in terms of D? What is the pole pitch?
Yes.
Yes. So pole pitch is nothing but like the same expression, right?
Pi d by P.
Pi
L
D
by
by P.
P.
Pi D by P. Right?
Yes.
1.5 into pi into D
Divided
by
by
4. And
1.178 L by D ratio.
yeah, L by D ratio is
Oh,
1.5 pi by 4.
4. It's a 1.178.
1.17.
8.
Yes. So now this expression we have, and on the other hand, do we have pi m? So yeah, mm, right. So im expression is nothing but 0.5 pi by 4 dl, and here we can plug in this L and D value, right?
How
So
L value we will
still
replace?
we are missing one expression.
One expression. Yes, sir. We need one more expression for finishing.
Still we need one more expression because we don't know here phi m. So what would be the next expression from where we get the dimension of the machine? We are given power, right? We are given speed,
Speed.
so we can calculate torque, and torque is directly proportional to d square L.
D square L.
Okay.
Okay. Torque.
So torque is nothing but power.
P equal to
Power
omega.
11
So
HP. So 11 HP will be nothing but how much kilowatt? Point 0.746 or something, right? 0.746 into 11 divided by omega is nothing but 2 pi into 1500 by 60. So this is your torque space. Okay.
yes. 0.746 into 11.
How much will it be?
It's 0.0522.
0.0522. Okay, so it means you are not considering 10 raised to power 3 part because horsepower is nothing but in terms of kilowatt.
Yeah, yes, yes, yes. Into Q will come.
So 52.2 Newton meter is the torque of the machine. Now torque is pi by 2 B into A d square. D square, and L further we can write in terms of D, that is 1.178.
Yes. 1.178. Yes, sir.
Yeah,
Correct, sir.
right. So 52.2 we can equate with pi by 2 into 178 into D raised to power 3. So from here we can calculate the value of D.
Hmm. 0.131
0.131 is the value
meters
of B.
diameter.
Yeah, it is around that. Yes.
Can I check one second?
Yeah, I am also getting the similar value. So
Okay.
it should be correct. Now from here we can calculate L, which was 1.178 into 0.131.
0.154.
At the limit 0.154, I am getting.
Actually.
Yeah. Okay. So now we have calculated L and D. So we can calculate the flux, maximum flux in the motor. 0.5 into pi divided by 4. L is 0.154 into 0.130. So can we get to calculate this value?
Yes, sir. (7.922 into 10⁻³
Exactly, 7.92 milliweber.
milliweber? Yes.
So we have calculated this value. Now I think we will be able to calculate number of turns per phase if we plug in this value here. Okay, so number of turns per phase should be 4.44 into 50 into 5m is 7.92 into 0.955.
247.15.
247.15. Okay, so ideally we can take 247 or 248 number of turns. Okay. So this is all about this problem. Any final question regarding this?
No, sir.
Oh, So next problem is with says method. We have to calculate the air gap. We are given the dimension of the machine. Again, air gap we have to calculate. We are given a dimension as diameter. Bore diameter is 0.145 meter and length is 0.17 meter. I think we can calculate. G is nothing but 0.2 plus
2 into L into D.
exactly.
Zero 0.514.
0.51.
51.
So this is the air gap for this dimension using Say's method. Here, if you want, you can calculate with Lipol method as well, right?
0.514 meters, sir. Okay.
0.51. Oh no, sorry, 0.51 millimeter.
Yeah, ma'am. Actually, we didn't put that much of air gap. No. Anyway.
Yes, correct.
But here it's a in meters. Yeah, length in meters, diameter in meters,
Diameter is in meters, yes,
length in
and
meters, and
yeah,
point
so
here some constant came, so it will come in meters only, na? No,
into 10 to the power minus 6.
-6.
So now, if you take under root, it will come out 10 to the power minus 3 outside with multiplication into 2. Isn't it? Let me 0.2 plus 2 times
Something is coming different.
0.157 into 10 to the power minus 3. Okay. So into 2 plus 2. Yeah,
4, 5.
it is coming 0.514 mm only. This is also in mm. Yeah.
Okay. Okay, then fine. But I'm getting 0.2.
You are getting 0.2.
Yes, sir, 0.2 I'm getting. First one 0.145 into 0.17.
Yeah. So under root,
And
if you calculate with this, how much are you getting?
6. Under root I'm getting 1.57.
Yeah, 0.157.
Okay, 1.57 into 10 power minus 4
Okay, yeah, that's
under
correct.
root.
Yeah,
So
that's correct.
answer into 2, 3.14 into 10 power minus 4. Answer plus
See,
0.2,
you are
0.206.
getting, see, you are getting with under root 1.57 into 10 to the power minus 4. Okay.
Hmm.
If you multiply under root of 0.145 into 0.17, that's fine.
Fine. 1.145. Sir, under root how much you are getting, sir? 1.57 into 10 power minus 4.
1.57 into 10 to the power minus 4. If you
Under
remove
root.
the under root. Yeah, if you
Under root.
remove the under
Yes.
root. Yes.
Yes. It,
Yeah.
and
Now you
answer
convert
to,
into 10 to the power minus 3 to convert into mm.
okay.
So
Here
1.57
we
is
have
nothing
to
but
convert into mm also, na? Okay. The mm for converting that one, we are putting 10 power minus 6 from meter to mm.
Okay. Let me simplify it. Okay, just
Yes, please.
let me recalculate. Okay, this is 0.2 mm plus
Okay.
2 times. If you multiply 0.145 into 0.17, you will get
24.67 into 10 power minus 3.
0.264
0.26.
into 10 to the power minus 3 is out of the under root, right? So it is also in mm. If we remove 10 to the power minus 3, it is in mm, right?
0.145 into 0.17.
Yeah, you will get this value.
No, 0.024 है ना?
0.024.
Actually, 0.145 into 0.17 is 24.65 into 10 power minus 3 means 0.024.
Okay. Yes. Yeah, it's my bad. Yeah, 0.0245, 0.02465, right?
But yes,
Right. Now, if we under root this value, how much are
mm.
you getting?
Under root 1 second. 0.157.
0.157, right?
And 10 power minus 6 is there, na? That is there 10 power minus 3 because the root.
So this 10 to the power minus 6 is converted to mm.
Hmm.
10 to the power minus 3. See, if you take under root of 10 to the power minus 6,
It's a
right,
10 power minus.
it will be 10 to the power minus 3, isn't it?
Yes, 10 power minus 3.
And if you take 10 to the power minus 3 and you convert into meter, it will be mm.
Again, we are converting to meter.
No, it is already in meter. This
Hmm.
parameter is already in meter. I am just taking out of it and I am naming it as mm. And I am eliminating this 10 to the power minus 6.
Hmm.
If you want, you can carry here. Okay, you
Okay.
can carry here. Okay, now you calculate. I think it was fine. Yeah. Now can we write like this? Into 10 to the power minus 3. This is
Hmm.
meter. This is mm. Okay. Is it
Okay.
fine till now?
Okay.
No.
Hmm. Actually, we are converting to meters. Already it is in meters. We are converting to mm means we can put positive, no? 10 power 6.
Uh, See, here it was in meter and 10 to the power
Hmm.
minus 6 was there, right?
Hmm.
And if you are converting to meter, sorry, you are converting from meter to mm.
Meter to mm means positive, no?
Yeah. So let's suppose it is in meter. It is actually in meter. Okay. So
Yes.
what can you write? You can write this much into 1000 mm. Can you write?
Hmm. For 1,000.
Right?
Yes, correct.
So
I
this
can do.
and this will be cancelled out.
Okay.
Are you following this step?
Yes, sir, I can
Hmm.
test.
So, so now
Finally,
everything is in mm.
0.514.
0.514.
Earlier also same one.
Yeah. Actually, I directly rewrote 10 to the power minus 6 to mm. If you eliminate 10 to the power minus 6 from under root, you can directly write as mm. Just you
Okay.
do manipulation in units on your own, you
Yes,
will
sir.
get that.
I think.
Okay, so moving on.
Mm. Seventh question.
So seventh question here. A stator of a machine has a smooth surface and a rotor has open slot type. A stator has smooth surface, rotor slots, open type. Okay. Now slot width is given how much, which is also given is equal to tooth width.
Slot width equal to tooth width, sir.
Yeah, in this particular problem, it is given, which is equal to 14 mm. It means ki slot ratio is 0.5, which is nothing but slot divided by total slot pitch. Okay. So in a
Okay.
slot pitch, half of the part is slot and half of the part is tooth. So that's why it's 50%.
Mm.
Now air gap length is given 1.8 mm. Okay.
Okay.
We have to find the effective air gap length using Carter's coefficient formula. Okay. What is the Carter's coefficient? Which is nothing but 1 divided by 1 plus 5z
Yes, sir.
divided by ws. That is slot width.
Slot width.
Okay.
Gap. Yes, sir.
So can we calculate effective air gap length?
Yeah.
And why effective air gap length is different from the air gap which is designed physically? Do you have any idea?
Uh, Effective air gap means after sleep we are using utilizing the air gap, that one. No. Normally, if you consider air gap is different. Like
Let's suppose we have a stator tooth like this, okay, and
okay.
slot. This is
Mm.
tooth, this is slot for the stator. Now
Mm.
we have a rotor tooth like this, okay. This is again tooth, slot.
Slot.
This is for rotor.
Mm.
So flux is supposed to flow from a stator to rotor like
Mm.
this in
Mm.
north pole and in south pole other way around like this. Okay. So
Okay.
ideally all the flux should flow from here to here. So effective physically designed air gap will be this much, which is nothing but given in this problem as how much?
Uh,
1.8 mm.
1.8.
Yeah, so this is given 1.8 mm. Now what happens because of fringing effect? If you can recall that if flux is coming like this and some flux will start traversing in this manner. So now how much is air gap? It is definitely higher than this,
Mm.
right?
Yes.
If flux is originating, you know, inside from inside and going to beyond the air gap and then entering the teeth, then it means it is traveling more reluctant path compared to the this designated path because
Yes.
of the fringing phenomena,
Fringing
right?
effect.
Because you do not have control over all the flux lines. Some flux are supposed to deviate get deviated from their original path. So that is why fringing happens, and that is why to incorporate that into analytical equation we use Carter's coefficient.
Okay.
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 So now, what will be the effective air gap length? Coming back to our problem, It is nothing but kg into z. So kg is the effective air or gap concentration factor, right? If you might have gone through the lectures. And this
Sure.
kg comprises of two parameters, right? One is the gap concentration factor for slots, and other is the gap concentration factor for ducts,
Mm.
right? So
Yes.
kgs, kgd. And here we have to ignore the gap concentration factor for ducts. So you can consider it as 1. So here kgs into g. You can calculate kgs. Okay, so what is the gap concentration factor for slots expression? If you refer the lecture, you will find this expression as ys divided by ys minus kcs into ws. Okay,
Yes.
so ys is nothing but a slot pitch,
Mm.
kc is nothing but the Carter coefficient, and ws is nothing but the slot
With
width.
what width?
Yeah. So can we calculate kgs from here, from the given information, whatever is given in the problem?
KCS.
So slot pitch is nothing but how much? It is slot width plus tooth width, right? So
Mm.
this
Yeah.
is not, this is slot width. From where this
Yes.
slot is starting
28
till
megahertz.
till till the next slot is starting.
When slot is started, that is a slot pitch. Yes.
Yeah. So 14 plus 14.
28.
So it is 20, 28. Right. We have to
Mm.
calculate KCS. So KCS expression is given here. We can calculate 1 divided by 5z. Z is nothing but 1.8.
The width of
And
the slot
slot width is 14.
15.
So this KCS will be how much?
Into 1. 0.608? No.
Exactly 0.608. So this KCS is 0.608, WS is 14.
40.
So it will be equal to 28 divided by 28 minus 0.608
Answer
into
into
40. So how much will be KGS?
it's a 1.4375.
1.4375.
Oh.
Okay, so definitely it will be higher than 1, right? So
Yeah.
that the effective air gap will be higher than the actual air gap. So our effective air gap length is 1.4375 into 1.8 mm.
Yes. 1.4375. Mm. Hello?
Yeah.
Yes. Yeah. Okay, sir. I thought that maybe I disconnected that.
Okay. How much did you calculate?
Into G. Yeah. 1 second. Answer into 1.8. It's a 2.586.
2.586 exactly. So because of this fringing phenomena, your air gap, effective air gap is way higher than whatever you designed for. Right. So that's why this factor you have to take into account.
Okay.
Okay. Any
Yes.
final doubt in this part?
No.
Okay. Okay, so next problem is we have to calculate the rotor bar current.
Eighth question. Ninth. 7. 9. Parts.
Three phase, 3000 volt, 260 kilowatt, 50 hertz, 10 pole, SCIM is given. Right. Internal diameter of a stator is given. Internal diameter 75 centimeter. Okay. Gross length of a stator 35 centimeter. Slots, the stator slots 120. Conductors per slot is 10. Winding factor is 0.955 and winding factor for rotor is 1. Why? Because it is a solid bar, so rotor slots is equal to 115. Efficiency you can take as 90% and power factor you can take as 0.9 lakh. So we need to calculate bar current here. So if we have all the parameters and we can calculate the rotor current and we have expression which is derived in the lecture in terms of rotor current, right?
Okay.
So I think we can calculate with the help of that expression. So the first thing is that we should calculate the stator current, right? Full load stator current should be how much? Since we are given with the all parameters, I think we can calculate the stator current, right? So that you can refer the stator current, or if you are not given the losses, you can approximate also how much the percentage of stator is going to the rotor, right? So for a stator current, I1 should be equal to P input divided by root 3 into V input into how much?
Root 3 VL
Power.
cos.
Power. Okay. Also, if you are going for the output side, so I think since we are given the rating of the machine, which is nothing but the output of the machine, isn't it?
Yes. 260 kilowatt.
So efficiency into cos 5
Efficiency cos.
into root 3 gain. So can we calculate I1? Which is nothing but 260 kilowatt
60 by root 3 into input voltage 3. Perfect. 0.9. Yes.
into 0.9 into root 3 into voltage is 3000 volt.
Yes. 10 cube. 61.774.
61.774
Correct, sir.
amps.
Oh, ampere.
Yeah. So we have calculated stator current at full load, right? So now we can approximate, since we are not given with the uh, specific losses, whatever is happening in the stator resistance and reactances, right? So
Mm.
generally we consider 85% efficient or 90% it is mentioned, right?
Mm.
So I2 dash rotor current, how much can you consider? Mm, Consider zero point 0.9 since 90% is given. 0.9 I1. All up to you, like 85%. So
So 55.5.
if you consider 0.9 I1, how much the rotor current you are getting?
55.59. If I took
54.
0.9 as, yes,
Yeah, so 55.9.
59. Oh,
5. Okay.
5.
Okay.
And if it is a 0.85, then it is 52.50.
52.50.
0, yes.
Okay.
This
So,
I would dash.
so let us go ahead with 0.85. That will be required to solve your assignment. So consider 0.85 for your assignment. So
Okay.
I2 dash is 52.50 amps. Okay.
Okay.
Now, bar current relationship with rotor current is given as Kw1 or Kw stator divided by Kw rotor, okay, into number of slots in stator divided by number of slots in rotor into number of conductor in stator divided by number of conductor in rotor. Okay, so these three factors you have to consider. Now, KWS is given 0.955.
Mm.
KWR is mentioned as 1. Stator slots is 120. Rotor slot is 115. Number of conductors, how much? Conductors per slot in the stator is 10.
10.
And how much is the conductors per rotor slot? How much?
10 here per slot 10. Total slot 120.
Yeah,
120. 1200. Total conductors 1200. Double layer winding.
yeah.
Total
So
one.
please repeat once more. How much?
1200.
No, no, no. See, yeah, 1200 is the total conductor.
Yes, the total conductors, sir.
Hmm.
For phase 1200 divided by 3. 3 12.
Okay.
So 400.
Here, Z1 is we are referring with conductor per slot.
Conductors per slot. Okay.
Yeah.
So here conductors per slot you already given 10.
Yeah, for the stator it is 10. How much for rotor? In the rotor we have bars only, right?
Yes, rotor bars only.
So bar is nothing but one solid conductor. That's
One
why we have
solid
to take one.
one.
Yeah.
Yes, solid.
So this will come out to be
0.955 into 120 into 10. So 9.965.
9.965 exactly. So now we can calculate bar current, that is I2 dash, which was 52.5
50.5.
to 9.965.
965.
It
It's
is
a
5.
522.17.
Yes. So see, even though input current is so small, 60 or 55 amps, your bar current is so high, right? So your bar is a solid conductor. That's why it can endure such a high current. Okay.
Okay, sir.
Any doubt in this part? Anybody?
No.
So let's move on to the next part.
Mm.
We are given different values of MMF, right? MMF for air gap, stator teeth, core, and all. We need to calculate magnetizing current per phase. In induction motor. Okay. So MMF required for air gap is 170 ampere turns. MMF required for stator teeth is 25 ampere turns. MMF required for a stator core 12 ampere turns. MMF required for rotor teeth 19 ampere turns. For rotor core it is 8 ampere turns. So that's all core area is mentioned here. Okay. Now a stator winding factor is given as 0.933 and turns per phase is 416. Okay. So now can we calculate magnetizing current?
Ampere turn. NI. We know all the NIs, no?
Yeah, we know all the NIs. Yes. Rajni, I think there is a lot of noise coming from your side.
Sorry, sir. Yeah.
Yeah, so whenever you are not speaking, just please mute yourself. Thanks. Okay, so let me give you, I hope you have noted the data, right? So magnetizing current is nothing but total MMF divided by number of turns. Okay. If you will calculate, RMS value of IM, that will be nothing but total ampere turns divided by number of turns into root 2. Okay. Now, magnetizing current per phase can be related with this ampere turns loading, and ampere turns loading is ampere turns amplitude loading, because if the flux is sinusoidally distributed in terms of MMF, so its expression is derived as 2.7 times Im T phase into winding factor divided by pole, number of poles. Okay. and it will lead to magnetizing current per phase 0.37 into P into ampere turns peak, okay, into ampere turn peak divided by T phase into kW1. Okay. So now if you will manipulate it, the peak MMF related to RMS value of IM, okay. If you calculate RMS value of magnetizing current, whenever you will be asked in the problem, you need to provide in terms of RMS. So that will be equal to 2.7 into IM into T phase into kW divided by P. Sorry, this is ampere turns. Here IM is nothing but RMS. Okay. So if you want to now let's go back to the calculation of this particular problem. So total, first we can calculate total MMF required in the machine. That is, we have to calculate all the MMF. We can add individually. So it is 234 ampere turns, right? Now, a magnetizing current, if we are providing here, that is nothing but 0.37 P into ampere turns divided by kW into TPH, right? And if you take the maximum value, that is nothing but root 2, so it will be how much? I am magnetizing current amplitude. You need to calculate amplitude or magnetizing current per phase. That will be ampere turns maximum or its magnitude divided by P into 0.427. 0.427 you will get if you do if you take 1 by 2.7 and you multiply or divide 2.7 by root 2, you will get this value divided by kW into TS. Okay, so yeah, I hope you are getting till this point, right?
Yes, sir. Get it.
Yeah, yeah. Ampere turns is 234. Number of poles. Okay, number of poles I didn't mention, so P will you can take as 4 into 0.427 divided by winding factor is 0.933 into turns per phase is mentioned as 416. This will come out to be Magnetizing current per phase. So after calculation, please let me know the value.
It's a 1.029.
1.029 amps, exactly. 1.029 is the value.
Just seven.
Okay, so I hope you will be able to solve all the problems given in assignment week 4.
Okay.
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 Uh, One final question is related to cogging and crawling. So that 10th problem, right?
Yes. Hello, I got 10 minutes.
So a status
Hello.
slot. Yeah, hello. Yeah,
Sir, actually, I have joined somewhat late. So, just I want to see the lipose method if you have already discussed. So, can you show me that slide?
sure, sure, sure. Yeah, so here with Lipos method we have calculated. Are you able to see?
Yes, sir.
Yeah, so a Lipos method is nothing but pole pitch into under root 2 times pole, number of poles, into 3 into 10 to the power minus 3.
Hmm.
Okay, so in the problem you are given with pole pitch and you are given with the number of poles, right? That's sufficient to calculate the air gap by Lipos method.
Okay, sir. Thank you, sir.
Yeah,
And one
welcome.
thing, the square you have made, that is the gap is equal to in lipose method. The unit will be in mm.
Yeah, the unit will be in mm. Where here you are saying in sales method, right?
Yeah.
Yeah, so see 0.2 is mm here.
Hmm.
Okay, and this value, whatever will come in terms of meter. So you will have to convert into mm.
Clear, sir.
Okay.
Thank you.
Or in other words, if you plug in the value of D and L in mm, you will get in terms of mm.
Yes.
Okay. Any other doubt?
No, sir. Thank you, sir.
Yeah, welcome. Okay, so we are going to discuss related to cogging and crawling, right? So what is cogging and crawling? Do you have any idea?
I think, sir, it is related to the slots of rotor and stator magnetic locking.
Yeah,
Um,
yeah.
um,
So basically, because of cogging, right? Why cogging happens? Cogging is also called as magnetic locking, right? Or tooth locking. So if a stator and rotor slots are equal, right, or ratio is such that both are aligning very frequently. So the alignment position or this position, as I showed you, right, that is very least reluctance path. So the rotor would not want to leave that position, and it will require higher torque, higher starting torque. Right? So let's suppose, yes. So whatever I have shown here, so this is a stator teeth and this is rotor teeth, right? And both are aligned here. So and because of magnetic coupling, this rotor does not tend to move forward, and that happens because the stator slots and rotor slots are in equal number or in some multiplication of 6, so that we will give the value whatever is the value required to avoid those lockings, so that is known as cogging, right? Crawling is that uh, when your induction motor runs at a speed lower than synchronous speed, right, at very low speed, and because of in harmonics in a stator mmf, because with the help of mmf distribution in the teeth, you are not only producing fundamental component of flux, you are also creating multiple harmonics. So the seventh order harmonics creates force in the opposite direction of the fundamental, right? So uh, the seventh, like ns plus 1, 6 ns plus minus 1, the dominant harmonic 6 ns plus minus 1, right? So 6 ns plus 1 creates force in opposite direction, in opposite of fundamental. And at low speed, what happens? Current is the function of slip, right? I2 is function of slip. So at low speed, your magnetic flux is already low, but seventh order harmonics flux is almost comparable of fundamental. So what happens that this harmonics is acting in opposite to the fundamental, and your motor starts crawling. Like it does not start rotating smoothly. It tries to smooth forward, but it does not happen very smoothly. So that is why it is called as crawling. And it happens because of the seventh harmonic and also at lower speed. And to be precise, 1/7 of the synchronous speed, right? You can either Google it or you can see the textbook to understand it in detail. But that's what, in nutshell, whatever I have explained. Are you able to get this idea of crawling and cogging?
Yeah, got it, sir.
Yeah, great. So, because of cogging and crawling, we do not keep the number of stator slots and rotor slots equal. Okay.
Yes.
So based on that, one problem is given that number of stator slots is 54. Number of rotor slots is 36, and number of poles is 6. Okay, it is a three-phase induction motor. So, which phenomena will be prominent? Whether crawling and cogging phenomena will be dominant here in such a combination of slots and poles?
No.
So the condition is the difference between stator slots and rotor slots is 54 minus 36, which is equal to 8, right? And since we are given with number of poles, so it should not be multiplication of poles. It should not be a factor or product of number of poles, right? 18 divided by 6, so you are getting 3 times. So there will be 3 instant where a strong cogging will happen in the machine. And at a speed lower than the synchronous speed, at very low speed, this phenomena will also, this factor will also implement a strong crawling. So that is why we should not have the difference between stator slots and rotor slots in terms of multiplication of number of poles. Okay, so that is why this selection should not be appreciated in the design of induction machine. Okay, so you should not go ahead with such a design if you are going for 6 pole. Right? So such kind of problem you will also see in your assignment. Yeah, I think the same problem is there in the assignment, right? Yeah. So I hope you got the answer. I was trying to
So
give you
that
an
is the
idea.
coding now, sir.
Sorry. Yeah.
That is coding is more prominent.
Yeah. Cogging and crawling both are prominent here.
Okay.
I think most of the assignment problems have similar data, whichever we took to solve the problem today, right?
Okay, we
So
didn't.
it yeah, so it will be a cakewalk if you just follow this, right?
Yes.
I think exactly same, all the data. Anyway, this is what they have provided me, so I do not have any excuse.
Sir, I have a question. No?
Yeah.
Actually, no, no, not related to subject. Assignment, they will release no assignment answers
Yes.
because I applied for both electrical missions too also, but I'm not appearing for the videos. That's secondary, and I'm getting the notification that really solutions are released for assignment one. Solutions are released for assignment two.
Yeah. So solutions are related. It means solution must be, provided in terms of PDF or something, right?
But coming to
Because
our electrical missions design, there is no any solutions are provided. No solutions. There is no any nothing is there like.
this subject you are saying, right?
Yes, yes, this subject.
Yeah. So I also haven't received any notification regarding solution, but answers
Yes.
are provided, I guess.
Answers are provided, but whenever they go for the assignment checking, na, there whether the answer is correct or not, they give some bandwidth and they will check that answers we have. That answers is
Okay.
there. But coming
I
to electrical missions too, we are receiving the solutions also, like the steps and all these things. Like,
Okay. I hope you will also receive for this course as well. I think it's just a matter of time, or either you can write a mail to them,
okay, okay, okay. I'll.
or there is a Q&A session, right? So
Yeah,
there
it
you
is.
can ask.
Yes.
Yeah. Okay. So any final doubt or any other doubt? I hope week 4 assignment will be done, right?
Yes, it's already done.
Yes.
Good.
So were you able to solve previous week's last problem based on DC machine? This generated EMF per conductor, total flux generated. Why that correct?
Total flux calculated, and coming to conductors and the last one, I EMF. I
Did you make any mistake, silly mistake, or something else? You did not get the
flux is
concept.
okay. Actually, thing is, we are the designers of BLDC motors, sir, mostly.
Okay, okay.
So
You design BLDC motors.
yes, yes. I used to design BLDC in MotorCAD, Maxwell, and Flux. And sometimes I used to go for the analytical calculations also. So that's why I know this electric loading, magnetic loading, and few other
Okay,
basics.
okay, okay. Impressive, impressive. So you
Um,
are a working person or you are studying somewhere?
no, no, no.
You
I'm
are
working.
you are working in some industry, right?
Yes, I'm working in automobile industry.
Okay. Where, if I may know?
Pune.
Pune, Pune. Okay, nice. In which company, if I may ask?
Yes, sir. It's a Flash Electronics. It's a
Oh,
Bajaj partner actually.
Bajaj partner. Okay.
Bajaj partner. We are working with that for designing traction motors and magnetos, ISCs, integrated starter and generator.
Okay, that's great to know because it's really fascinating if they are manufacturing motors here in India. So
Um,
you might be facing some challenges also, right?
of course, that's why while I'm doing winding because I'm not the winding means winding man means I'm not wound the mission, but I saw I will design the mission and I give it to the people.
Hmm.
They used to wound the mission, and at the time they told, "Madam, please don't keep this much, don't keep that much."
Okay.
Okay, we used to face real challenges over there.
So mostly you guys design concentrated winding or distributed winding?
Concentric, mostly concentric. All the traction motors are concentric.
Yeah, that's very
Concentric.
convenient also. And this BLDC, you mean a square wave or trapezoidal current, right?
Hmm.
Trapezoidal current or also sinusoidal current?
Sinusoid.
Sinusoidal current.
There's a
So in
controller. They will take care of by electronics department. They will take care like what
huh,
when to on, when to off, and we are taking care about the windings and how much slot pole and what is the air gap. All these things, basic things.
that's correct. But according to the current requirement, like if you are designing for concentrated winding, it means
Mhm.
it is more suitable for trapezoidal waveform of current. That's why BLDC.
Actually, they what we mostly this magnetos, so, so generators what we are using in our missions. So they will give a DC side mostly. We want particular RPM, we want this much DC current. Like that, they will give to us. So based on that data, we use it to go for the designing, how much diameter, how much length,
Hmm.
this all
Okay,
these
okay.
things.
Nice to know. Great. So you can also provide some insight to us if you are,
Of
either
course.
designing or
Yeah.
something. Yeah.
Yes, we
So
can.
you prefer designing in you are aware with MotorCAD, Maxwell and Flux,
Yes,
all
yes,
three
yes.
software.
MotorCAD, I know. Initially, we go for the MotorCAD. Once we finalize in MotorCAD, we go for the Maxwell and next Flux, Altair
Okay, so
software.
you validate in all three softwares.
All the three softwares.
Right, right. Nice approach. Great.
And this is very important. Like, I feel very happy, sir, because something, okay, while we are designing, we mostly focus on softwares, not that much data, but it is giving to me data also. Like,
Hmm,
it
nice.
gives deep idea about analytical for me. Actually, that's what
Uh-huh.
I think.
So, like from the status side, whatever we are studying for induction machine, that would be applicable for also BLDC.
BLDC also. Yes, yes, BLDC
Yes,
also.
yes. And regarding rotor, I think sometime we can discuss. I think in this course there is a BLDC section or PMSM section.
BLDC is the axial flux missions also. That is a new trend actually, axial flux missions.
Hmm.
That one also included in our section actually. I saw that one.
Okay, nice.
Last one is they want to speak about the axial flux missions.
Okay, and
Last one.
uh, in your company, some people come to discuss something or explain something you are referring to.
Means not getting
Uh,
once again.
who are you referring to? They like they come to show axial flux machine.
No, we will get some samples and we use it to make some samples of.
Also, so you are saying that you guys have a sample of axial flux machines.
We'll get some samples. Yes, samples
Or samples
and
from your company or outside your company?
no, for inside of company only we will take.
Oh, oh. And is it big enough? Or how much rating approximately? Do you have
Rating
any?
actually, I'm not very sure. Because currently we are not manufacturing axial flux machine. Just there is some testes went on. I think two
Hmm.
years back.
So you guys manufacture all the machine components in-house?
In-house motors,
In-house.
electromagnetic parts, and electronic parts also is there. We are not taking care of. I am from R&D actually.
Oh, nice. So electromagnetic part, you mean a stator core, rotor core, winding,
Core,
magnets.
rotor core, motors, ISEs, magnetos, like these all, and ignition coils. That is nothing but transformers. So that's all the things that we will take care. And coming to electronic part, electronics department separately it is that they will take care programming and all these things.
Okay, okay. Actually, why I'm very much curious about this thing. Recently, I have fabricated a PM-assisted synchronous reference motor.
Okay,
So in that, we have faced certain challenges regarding manufacturing. We have manufactured in Thane here in Mumbai.
okay,
Okay, so we have one thing what we observed for distributed winding, we went ahead and we faced a very less slot fill factor, around 34-35%.
oh,
And
I think
if
wider more no.
yeah, required desirable, it should have been, yeah, zero point 0.4 to 0.43, but zero point 0.4 also should be acceptable. But
Okay.
0.35, it is a bit, inconvenient to give it to industry person, right? So I was developing for prototype, but
Mhm.
that's the bottleneck as of now we are facing.
Okay, we use it to do 2 wire diameter also, so to 1.5 with the two parallel path like that we use it to do.
1.5 mm of wire diameter, you are saying, right?
1.5 and 2 also. Just recently, I designed one is a 2 wire diameter. That's what actually while doing winding of 2 it's very difficult them to keep 50% I took actually slot wheel.
Uh-huh.
They unable to wound. They told that 1 or 2 tons must be less because of tension and we took hand winding. No,
Hand winding, right?
it's very hard to do hand winding. So again, I changed to 1.5 and the suitable number of turns. Again, I did the simulations over there. Thermal analysis is very important for us.
Okay. Okay. So maybe I'll reach to you or your company regarding manufacturing. So you guys develop prototype also for like us, people like us.
I don't know, sir, because I'm engineer actually, senior engineer, and they will take care of it. Total vice president, where like, seniors are there.
Okay, so it will be really convenient if you share the email of them, like whoever is the concerned person for prototyping.
No, actually, for bulk amount only they will manufacture because I used to see in R&D, even they didn't allow anyone inside the R&D. I don't know what is
Okay.
the exactly thing.
Hmm. Just they
Just
do not want
interns is
anybody to
there.
copy.
Interns they will allow for 1 or 2 months, and otherwise they didn't allow inside anyone. No, access is not allowed.
Okay. So,
And
so
they
could you please?
actually bulk Bajaj is our customer, no? So we used to do like parts for them.
Okay, okay, okay. Great, great to know. So could you please again repeat your company name, a spelling?
Flash Electronics, FLASH. Can
FL, Flash Electronics.
yes, sir, Flash Electronics. You can
Is it
Google it.
correct? Yeah,
Yes,
yeah,
yes.
sure, sure. So anyhow, I have developed one prototype. It is working as of now, but still some drawbacks are there. So we are looking for better manufacturer here. So in manufacturing unit, actually we are currently lagging so much. Nowhere we are able to find perfect manufacturer as of now. Some people do winding well, then they suck in magnets and all. If some
Mm.
people do magnets well, then they do bad windings. So it is very difficult to find a whole manufacturer from that perspective. Yeah.
Yeah, I agree with you. Here, what happened? There are actually some companies are there. We are providing means motors and all automotive parts to them only, not outsider side.
Okay. So since you guys are already delivering to bazaars, so
Bajaj,
I
yes,
will
we are Bajaj
so
actually.
I believe manufacturing must be good.
Mm.
Sure.
So
That's
many,
the
so many parts are there. So many parts. The manufacturing lines are there. But okay, manufacturing and R&D is not combined. R&D is different place.
yeah.
But we used to
Yeah.
go there and we used to watch how they are manufacturing traction motors.
And they entertain like people from academia or research people. Do
Uh,
do they
for
entertain like
electronics, they
with
will come
discussion?
actually. For electronics, they will come. But coming to electrical and coming to winding, there is nobody